Division. So I know that right off the bat, I'm just going to say I'm not going to do justice for the other divisions there, but I'm going to try my best. But I did leave our web page up there if you wanted to go and research a little more, just a little bit about my background. So I've been with the department for 5 years, coming up here in December, 5 years. Prior to that, I had 10 years of experience working for the EPA in Dallas, and got some good opportunities there working in several other states, and have brought some of that knowledge and have learned a lot since I've been here. A little bit about the division. We're primarily a regulatory agency, so it's a challenge many times to balance promoting ag products and our Oklahoma agriculture while maintaining a regulatory arm. Doing that, we've got several divisions. We got 10 different divisions with the agency. So we got the administration division, which interestingly enough houses our criminal side of the Department of Ag. If you don't know, we have a civil and a criminal side for regulatory purposes. So we actually have agents that are dealing with livestock thief, livestock stolen livestock, stolen ag equipment. My division, the Ag Environmental Management Services Division, which is a mouthful, so we generally just refer to it as an acronym, which is the AIMS division. I'll talk a little bit more about, so my division, we generally license and inspect animal feeding operations in Oklahoma, and associated with that, we do a fair amount of work with groundwater and surface water related activities through nutrient management plans, carcass disposal plans, and how that ties in today's topic is ensuring that lagoons are not compromised and not leaking, and if they are, making sure that we receive corrective action plans, we review them and make sure they're appropriately addressed to address the issues on the farm. Carcass disposal plans, making sure that mortalities are being managed in appropriate manner so that it's not impacting groundwater and surface water or any other resources. We have a statewide sampling plan that we work with the Oklahoma Water Resources Board. Samples around somewhere, we've got 900 plus wells in Oklahoma, monitoring wells around the swine lagoons, and at any time of the year we're sampling about half of those have enough water in them to be sampled for groundwater purposes. We've got focus on, really our divisions that focus on water is going to be the Consumer Protection Services and Food Safety Division. One of the areas where they really focus on groundwater and surface water and soil is responding to pesticide spills or fertilizer spills, remediating soil, as well as groundwater impacts. And then our Laboratory Services Division, they serve as a support role for the agency, and so they're sampling feed bags, seed bags, weights and measures, calibrating weights and measures. So we have entity they'll bring their scales to our lab and have them calibrated and certified. But they also serve as a support role for the water and inorganic sampling that they do for some of the other agencies as well. They sample or analyze all of our 500 plus water samples a year that we send them, as well as any other support that we need for enforcement purposes. They provide that service for us. As well as the last one is Forestry Services. You wouldn't think it a lot, but they actually have a pretty decent water quality program where they've implemented best management practices through their forestry program as they are harvesting and managing forests in Oklahoma. They've got a water quality specialist there. Again, Dwayne mentioned soil health. They're very attuned to the benefit of proper managed forests through water quality to improve not only sediment transport, but also improve the soil health on site. And again, my time's coming to an end. I know that I've obviously left several things out, but I would encourage you to take a look at our webpage there to get more information. And I'm not going to take your agenda.
Thank you, Jeremy. So as you can see at the department at ODAF, they're doing lots and lots with water. And I've done research with them in the past with Kenny Naylor, one of his colleagues, and they're great partners, and they're taking lots of samples, have lots of data, and have lots of things going on. So they're also a great partner. And it may seem like you guys just got in here and sat down, but we are now at another networking break time. Let's see how we're doing here. 1:08. So if you guys could start coming back in about 1:30, we'll be pretty close. But this is a chance once again, and if you want to stick in here or go in the other room, that's great. Talk to these recent speakers, find the ones from this morning, or if there's something from this afternoon you think is really interesting. Let's continue those collaborations. Thank you, guys. All righty, it looks like we got most everybody back, and everybody else will be moseying on in here in just a second. But we're ready to move on to our next section, which is water treatment and remediation. We're going to start off with a whole bunch of engineers right after lunch, so that's pretty exciting, right, Mark? Yeah. Yes. All right. So our first speaker is Mark Nanny from the Civil Engineering and Environmental Science Department.
Thank you. My name is Mark Nanny, and I am an environmental chemist in the School of Engineering and Environmental Science here at OU. And before I begin, I'd like to acknowledge my other collaborators in this very interdisciplinary project, and that's Bin Wang, who is an electrical engineer, Joe Saflito, a microbiologist, and Ruzba, a petroleum engineer. And what we're working on now, we're in the early stages of building in situ Raman sensors, microchip sensors that can be used for real-time assessment of emergent and emerging contaminant mixtures, okay? Now, let me make sure here I got what is the challenge with these mixtures? Well, if you have regulated chemical contaminant mixtures, they're hard to analytically deal with. You have to go out, collect samples, do massive mass spec, extraction, all of that. Takes a lot of time, and it's hard to do a very spatial distribution. If you are talking about newly emerging contaminants, how do you know what's there? How do you identify and characterize them? So these are big challenges we're facing, particularly with mixtures. So what kind of infrastructure needs are we facing? We think the microchip Raman sensors we're proposing will fit this bill, and they can be validated and standardized for a variety of contaminant mixtures. They can even be calibrated for target organism response, so we can get an idea of how mixtures, as they change, could impact biota. And then finally, coupling these together in a network, we can get real-time data such that we can begin to model it and begin to do simulation and prediction type capabilities. And all of this will eventually be used for evaluating any kind of organic contaminants, whether it be treated wastewater or production water or whatever you have. Now, the design is, the microchip design, or this two-layered system here where water flows through in between these plates. The upper plate is a dielectric lateral grating, and the reason for that is we want to have our light waves trapped in these pores and bounce around and do some interesting things with the sample. The lower level is this material with gold or silver nanoparticles. Now, the idea is that when we irradiate this region with water flowing through, our analyte, these circles, will be interacting with the nanoparticles, which will be excited by this incoming laser light and create a plasmonic effect, which means that these things are going to be about 1,000,000 times more sensitive than a typical Raman spectrometer. And that light gets bouncing around in that lateral grating, and then the scattering is emitted for detection. And Raman spectroscopy is really exciting because it is not sensitive to water, and it can be used to detect a variety of organic compounds. This is some preliminary data where Bin has done some computational work showing in the bright yellow areas where the plasmonic effect would be really strong, right where we think it should be, and we've even started building some of the two-dimensional lateral guides that we're going to work with. Now, to kind of give you an idea of what we're thinking about, here's an example of a wastewater treatment plant. So you run a wastewater treatment plant, you are worried about what's coming in there, particularly maybe if you have compounds, mixtures that are going to impact your anaerobic or aerobic processes. So you could have microchip sensors throughout your sewage collection system that could alert you, be a sentinel, tell you if something's coming in. You could have sensors throughout the system to tell you how well your processes are performing to remove those contaminants. And then you could even have sensors in your receiving water to see what is happening as you go along. And you can even have these sensors calibrated to your anaerobic and aerobic microbes so that you know if there's something coming that's going to impact your biological system, you could perhaps turn on some ozonators or do something that would minimize the risk to your system. Another idea we've been working with is, for example, like in the Gulf of Mexico where you had the Deepwater Horizon and you have this petroleum plume going up to the surface. And each one of these different colored dots represents a different hydrocarbon molecule. As the petroleum plume moves upward, there's physical fractionation, as well as oxidation from photolysis at the surface in the microbiology. So not only do you have fractionation of the molecules, but you also have changes. And if we have sensors distributed in a network, say from buoys and detecting these things as a function of depth or even tethered, we can see changes in the different types of scattering bands as a function of depth in a different sensors. So this provides a really nice network that allows us to detect what's going on with the organic compounds and how they transform in the environment. So I'm out of time.